Good afternoon, everybody. So our next talk is going to be the Programmer's Cryptography Toolbox by Triss Healy. Over to Triss.
Hello. If it's not really obvious right now, this is my first talk. I'm a little underprepared, sorry. I'm Triss. Let's go info slides. Okay. Just a bit about me. I've been to LCA a couple times, but heavy procrastinator, I think, is evident. And I've been programming for a while, and I've just worked between different fields all the time. And so I've become I know a bit about every field, but I'm not a master of any of them. So I started trying to make games, and I got to Python, C, Go, Rust, and Haskell was all just uni, and then I just got a job in writing C# for a Windows CRM, which is in Windows, the OS, but it was a CRM for ordering Windows, so it's 2 in 1. And now I work at Canva, just work on our API infrastructure for public APIs. And I've always had a strong interest in math, but I kind of, that's me in math at college, at uni. And once I tried to get into the math, I just found it really hard, but I still had an interest in cryptography, so I'd go learn all the different algorithms, but not how to actually do any of the actual math of cryptography. So, skip ahead. So I've had a lot of time working with these libraries, and I have a little story to just get us into our actual topic. So, Canva has just been a GUI interface for a long time, and while I was working, right before I joined, they were like, we should have an API like Google Docs has, everyone else has, so enterprise businesses can automate a lot of Canva's functionality, just organizing their designs, all sorts of things. That's kind of valuable. So we start implementing an API. We use OAuth 2. Unsurprisingly, I'm not going to go into all the details, but we need API keys. An API key is most of the time just a password, which we did pretty well. I'm pretty happy with whatever my team did, which was generate a 32-byte key, very simple, and just encode in base64, give it to the user. We'll find out why we had a prefix. We also had a checksum, which is CRC32. I should point on the screen, that gets recorded better. But if you want to learn about OAuth and you don't know, I can recommend this PurpleCon talk by a friend of mine, also works at Canva. I'll post the links after the talk. And so what we do with our secret key to store it, we give them the API token because they need to use it, but we need to store it securely so they can send it to us. We can verify that it's the real one. But a secure way is just like a password. So we're going to use the password hash API, which Canva uses for their password storage. It's just a password. That's all fine. 1 year later, we get into this thing called the GitHub Secret Scanning Partner Program, which essentially when people accidentally upload their passwords all the time, they commit it they hard code it into their code, they commit it, push it up, or they think, oh wait, I shouldn't do that. Make a new commit over it, and it's like, it's not there anymore, and no, that's not how Git works. They push it, and the old commit's still in there. Classic Git stuff. And GitHub and some other companies as well thought it was a good idea to just set up this program where if we put the keys in this format that I mentioned earlier, it starts with a prefix and has a checksum, and they'll scan all blobs, commits, comments for those things that look like their secret passwords, and then send them to whichever company. So if you post your AWS secret to GitHub, GitHub will then send that what it saw to AWS, and they'll process it and look for it and revoke it. And fun fact, When we rolled this out, I was the first person to get paged for it. I was on call. So I just asked on Slack, it's like, oh, how do we revoke this? I was like, oh, just go in the database and find it, because there's a project to automate this. We haven't started it yet because we have too much to do. So let's just manually do it for now. So I was like, oh, yeah, just hash the password. So you hash the password, there's the password. Look up that hash. Wait, that format, if you don't know, if it starts with $2Y, that tells a Unix system what password you're using for a password. We're using bcrypt to store passwords normally. Bcrypt is salted. So you have a database with, I think at the time it was 100. We hadn't fully rolled out yet, but now we're in the several thousand. In order to find the matching password in there, a salt, which I'll cover later, means that each salt has a unique key, and in order to compare against them, you have to run through every single entry in the database, rerunning bcrypt. I'll put the rest in. Oh, I just said what I said. Prepare your talks beforehand. And another problem is, one, that format's not exactly that secret. I just told everyone. So someone can guess the format. You can guess it by just clicking on it, figure it out. Or you can actually just go get new secrets, and you can just keep posting them to GitHub really fast. And if we have to go through the database, scan the database every time to look for matching passwords, even if they're all fake, it's gonna create a denial of service opportunity. So pretty simple. We just changed the hash. It was a bit annoying because you had to do this whole migration thing. We have to wait for them to use it because we can't reverse the hash. We have to wait for users to use the key, go, oh, that's the correct one, update it to the new format. Other option is to encrypt the password. That means you don't have to do that, but then people can steal it easier. One thing I found when I was going through all this, I had to, one, figure out that was the problem. Two, explain that to one person, and then I explained it to another person, and then I explained it to I explained it to a lot of people before I told the whole team at once, and then realized that not just in this job, I've had previous jobs where every time I have to do something for cryptography, I have to explain every concept to every person I ever work with. And it just makes me now, at some places I think of like, oh, you're the cryptography expert. I'm not an expert. I don't really know cryptography. I just know how to use it a bit. But it does make me a bit authoritative a lot of the times because they don't even know how to research the cryptography. And I just want to get more information out there, make it more approachable to like, how do you use these cryptography tools? So I thought I'd start going over a few of them. As you may have noticed earlier, my slides aren't very finished, so I'm going to get like halfway through and then switch to my notes and ad-lib the rest. Feel free to ask questions, because then we might run out of time and I don't have to get there. Let's get your notes out. I like this definition of cryptography. It's a tool that turns your nice, lovely data into meaningless gibberish. It only sometimes let you turn it backwards, but a lot of cryptography is just going one way. So, you will hear this a lot. Don't implement cryptography. That doesn't mean you can't use cryptography, you can't use libraries. It just means don't try to come up with your own algorithms. Don't think, hey, if I RNG this and then just XOR everything together, that's well known and it's very easy to break, turns out. It doesn't mean don't try to implement crypto if you want. I've tried to implement SHA. It's actually really boring to implement. It's just a bunch of bit chips and XORs and stuff. But getting crypto code working and getting crypto cryptographic code into production safely is a big gap. It's that safety that is very hard to do right, because you don't know if you got it right until nobody breaks your code for a long time. Even then, it might have a vulnerability, it just hasn't been found yet. So the general advice is use a library. Here are libraries I recommend up the top. Open source, this is everythingopen, I prefer open source. Probably all heard of OpenSSL, and if you didn't hear it before for SSL, you probably heard about Heartbleed, which was OpenSSL, but it's still a good library, even though that was really big. LibreSSL was a fork of OpenSSL due to Heartbleed. It's maintained by OpenBSD team, who are very good. If you need more bespoke algorithms, NaCl and libsodium I can recommend. Libsodium is a fork of NaCl. NaCl is written by cryptographers. It's very hard to use. It just has a C interface. And anyway, libsodium is like a nice fork of it that makes it much easier, and you can use it from like any library you want. And this is the general thing of cryptography. Even if you're using the existing algorithms, it's very easy to use them wrong. Very easy. Often vulnerabilities in crypto aren't in the cryptography, they aren't in the implementation of cryptography, it's just handled incorrect. Libsodium and NaCl are designed explicitly to prevent you using it incorrectly. You can go through that documentation to see all the examples, and if you're in Go, that library is apparently very good. I don't work in Go, so I can't verify that. Ring is quite nice as well. It's not really written in Rust, it's mostly written in assembly, but it does have a Rust interface. And if you're on Java or C#, it's probably easier just to use your platform. And Windows and macOS also have their ones. If you're on mobile, you might have to use theirs. Hashing. Does everyone remember doing that? I guess at what the 5F4DCC is. Anyone want to guess?
Hunter 2.
What?
Hunter 2.
No. That would have been a good one. No. Close.
Password.
Yeah. It's password. Just as a tangent, because I love tangents, there's a thing in PHP that if the hash of something equals something that starts with 0e, PHP will then interpret that string as a float and convert to 0. Who thought that was a good idea? So, details of what hashing is. This example uses MD5. If you didn't know hashing before, MD5 is old, don't use it anymore. In fact, hashing MD5s for passwords, the first cryptography article saying do not use MD5 for cryptography or passwords was published in 1995 before PHP was invented. This kind of code was in probably every PHP app for 10 years. Again, why I'm giving this talk. Hash algorithms are notable because they're irreversible. It's a one-way encryption. This is a diagram of how SHA does things. Kind of, who knows? But the general idea is, I think these are in blocks, because this takes a 512-bit input, but that's not 512. It takes these blocks and combines them with various math functions. Ideally, these functions need to be really fast on the hardware, because historically people said, oh, don't use cryptography unless you really need it because the performance cost is too high. You want cryptography to be fast, so a lot of new algorithms, although that's SHA-2, it's not new at all, needs to be fast. Otherwise, people don't use it. So it is a bit of a trade-off, but it's better to design the algorithms to be as fast as possible. Generally, the idea is every bit of the input affects every bit of the output. So conversely, if you look at the equation for any bit of the output, so if you put in an exact 256 bits for SHA-256, and you get 256 bits out, each bit of the output would be a absolutely massive algorithm of every input, every bit in the input. So if you try to run it backwards, it would take you the rest of the universe to compute. 256-bit is a very big number, very big search space. So it's hard to reverse. Sometimes algorithms have weaknesses, notably SHA-1 and MD5, which is why they're not on the slide, because these are algorithms that are safe to use. Although these are the old ones. We still use these for everything, basically. But these are kind of the new ones. SHA-3 is the NIST standard for to replace SHA-2, hence the name. Blake 2 and 3 are kind of the cool kids, the new kids. They're based on Salsa 20 or Cha-Cha 20, one of those two. I only learned that today while researching this. Another thing is salt. That was always the advice, was to salt your passwords. I will talk about it in a minute of why salting is not good enough. But bcrypt had a salt. Bcrypt's a bit more than a hash algorithm though. You add randomness to prevent a lookup, like what we're actually trying to do in my story. But if someone hacks into your database, downloads all the keys, if they don't use salts, you do a hash, you hash every known password, every well-known password, or any random password, and then you can look up in the database. You can look in your big list of passwords for any matching one. So when you look password, you'll find all the passwords that are password. So randomness means you have to go to each one and try all the passwords of that one hash. So you have to try, it massively increases the cost of actually cracking it. Pepper's a bit different. Say you did have salts, computers are very fast, even with the cracking. You can still, you can still brute force it. You can brute force it smartly. So if you try password for every password, you'll find every use of the word password. What you can do for Pepper is, if you're hashing something, is you have a secret key that you add as well. And if someone steals the database by SQL injection or something, they don't know what to insert beforehand. So even if they try to crack that, they don't even know where to start. So it's like an extra salt that's secret. It's usually the same value for all secrets. It's too hard otherwise. But or it could be the other way is to derive it from the user ID with a secret as well. But the general idea is it's kept outside the database. It's somewhere else. So if someone steals your database, they can't really even brute force the passwords. Hashes outside of passwords that you don't use directly often use as signatures. I wrote this knowing I'd have to explain it in the talk. So this example is from Wikipedia. So this is someone's attempt at creating a signature with a secret key for a piece of data. So this up here is our data. That's our HTML query string. And we want to sign that to send it. So we're going to send this data. We're going to, before we hash it, we're going to add a secret password at the front. And it's going to produce this hash. Thank you. Now you all know when I'm flying home. Let's turn that on. And so we can send this hash and the original data. Now, this example uses SHA-1, I think. I forgot. Doesn't matter. It's a regular hash algorithms, whether it's SHA-1 or SHA-2, the old family of algorithms. What someone can do to attack this algorithm is they add a bunch of padding, and then waffle equals liege overrides waffle equals ego, so it changes the waffle order to a different brand. And all they need to do is SHA as an algorithm, I love hash algorithms, they do that math, and to get the output out, there's an internal state, and they just pull that state out, and that's the output. So what you can do is, if you have a hash, So this hash is part of the message, and you want to change that, is you take this hash and you set SHA's internal state to the previous output, and then you feed in the rest of that order, the waffle equals liege, and so now you can combine this data with this new hash, and it looks like a valid signature even though you never had the seeker in the first place. So we solve that with HMAC. HMAC takes another hash algorithm, so you'll usually see HMAC SHA-256 or HMAC SHA-2, which is the same thing. You can combine HMAC with any hash algorithm. Screen went off. It's back. Assume it's a cable, usually a cable. And HMAC takes the key as part of its algorithm, and it does some magic. I don't understand it, but it kind of weaves things together so that you can't do that length extension anymore. You can't reconstruct that state. So that's a SHA-256 bit of hello world with that key. This is all hex encoded. Cryptographers use hex encoding over base 64 as far as I can tell. That's where I ran out of time. So, one of the things I mentioned about hashing passwords is brute forcing. With our hash algorithms, as I said before, we want all the algorithms to be really fast. So a lot of hash algorithms are fast. MD5 was actually extremely fast, which is why it's so easy to crack, other than it being weak cryptographically. So our next trick is called a key stretching algorithm, or a KDF, key derivation function. bcrypt is the example I used in our story. It is quite good at storing passwords, sorry. So one way to prevent brute forcing is to find a way to make it just take too long. So if we take an algorithm we take the fastest way of calculating that, so often it's just a hash function, and we just repeat it a lot of times, say 1,000,000 times. We can now make the cost of computing it not only quite long. In the case of bcrypt, it could take 100 milliseconds for the default settings, which is 2 to the 10 iterations, so about 1,000 iterations. It now takes like 100 milliseconds to compute. So if you want to brute force 1,000,000 passwords, you're now taking 10 passwords per second. It's just going to take you a long time. That was part of the problem with our lookup before, is even if we wanted to do a table scan, which would be a bad idea, it would be really slow because we're doing it through bcrypt with strength of 12, which took, for 100 passwords, took a fairly powerful computer about 10 seconds to compute. So it helps for cracking passwords. You'll find that your Linux stores passwords in a similar form. I forget how it does it, but bcrypt comes out of BSD. That's how it stores your password. So even if someone gets your x/shadow, it's hard to crack your actual password unless it's a very obvious password like hunter2 or password or something like that. The main key stretching algorithms are, I got this exactly right yesterday somehow, it's PBKDF2. Good.
I've never been able to do that in one go.
That's my, I got first go yesterday too, and I was like, let's see if I can do it again. PBKDF2 is the kind of NIST, I think it's NIST standard, but it's the main standard algorithm. It's FIPS compliant. All that, everyone likes it. I think it's in a lot of the Wi-Fi security as well. It is just a slow algorithm on purpose. Slow on purpose. That's the whole point of KDF. It's called a KDF as well because when you want to encrypt something with a password, you put the password in and it uses KDF to create the key and encrypts the rest of the file with that key. It's also an RFC. I had to check that. It's RFC, if you want to look it up, it's RFC 2898. Yes, that's part of all those standard algorithms. I hardly ever use the actual standard algorithms, so it's not a big thing for me. I've lost my notes. So, probably when you come to cryptography, you're thinking about encryption. That is probably the main use of encryption. Cryptography is encryption, and an interesting thing about encryption, cryptography comes out of math. Don't need it anymore. Cryptography comes out of math, and there is an algorithm in encryption that is perfect. We can mathematically prove that you can't crack it, which sounds a bit weird because usually there's never a perfect answer. But there are problems with the answer. The algorithm's called a one-time pad. It is used a lot in actual espionage because they have the resources to actually implement this algorithm because it's very annoying to use. You know what? It's called a one-time pad for an important reason, but the idea is you start with your message, hello world, for example, and you need a key that has to be pre-shared, so both people need the key. It has to be exactly the same length as the input, and you simply take each bit of your message and XOR it with a bit of the key, and that gives you your ciphertext. It's very simple, very easy to implement. You could do it on pen and paper if you really have to. It doesn't have to be XOR, you can actually use it in other bases, but I don't want to go into the math. The problem is the pre-shared key. You have to share a key beforehand, and you can never use the same key twice. I got this story from someone offhand, so I can't really cite it. But there was a case of spies, I think they were Russian spies in Australia, where they were intercepting the messages that were encrypted, and they were like, oh, this is very annoying. But the cryptographers eventually figured out they were using the same one-time pad every day, so they just could XOR the previous day's message, and then you get the original. You get the key, and you can decrypt every message. That's the problem with the algorithm. Once you XOR if you XOR two messages, you get the key out. So you can't use the same key twice. The reason you can't brute force this algorithm is because there's as many keys as there are inputs. So if you tried every key, you'd also get every single message with equal probability. There's no information you can extract from it. So what you find is a lot of the algorithms I'm about to go through, which are block ciphers and stream ciphers, they're symmetric ciphers, are essentially coming up with ways to do an input instead of this massive one-time pad keys that start with a small key and create a big stream that you then XOR to your actual string. The most popular algorithm for encryption is AES. Usually you see 128-bit. There's AES 256-bit. That just means the key is 256-bit and it does something magic. And the AES is a US standard. It's the NIST standard. It was done as a competition, so it was a cryptographer outside of the US government submitted into a competition or selected out of several other algorithms like Blowfish. And AES is a block cipher. Well, what that means is it has a function, the AES function, and it takes a key and an input and turns it into an output. It's very similar to a hash algorithm, but that's not useful we have messages of variable length, so there's a lot of cipher modes. So you get AES, CBC, CTR. ECB mode is just XOR each key. It doesn't really work. It doesn't really provide security. You can crack it if you want. But the main one we want to use today is AES GCM. Actually provides another thing, feature, but I'll get to that in a minute. ASGCM, one of the challenges with the AES is it does have a lot of math and operations, so expensive to do on computers, like multiplication. How much time have I got left? I don't know when this finishes. 15, I see too much time. AES-GCM, and with AES-GCM, there's one of the advantages because it is so important and lots of things use it. Every time you use the web, it's probably using it for the internet, encrypted internet connection, is it gets a lot of attention and it still hasn't been broken, which is a great sign. But there is a vulnerability we do know about AES, which is say you have a virtual machine, it knows it's stored on the Linux kernel, it knows everything about the system it's on, but it wants to steal the encryption key used to encrypt the disk at rest. And the kernel, the host kernel, is using the Linux software implementation. I'm not sure if this is in the current version, but there are older versions where it's vulnerable to this. The issue is AES is kind of slow by default, but you can optimize it and make it fast, even GCM mode or not. The problem is the optimizations use lookup tables, and CPU caches mean that the amount of time it takes to calculate it depends on the secret, and you get a lot of timing attacks. So it's only recommended to use AES GCM when your hardware provides the algorithm under the hood. Well, provides a lot of the functionality you need to compute the algorithm quickly, so you get all sorts of weird, insane x86 instructions that don't make sense, but their entire purpose is to implement AES. But you can use them for other things that are a bit weird. So, after a lot of this was realized, the new algorithms were developed. I'm still in block ciphers. I'm missing a note. Blocks. I'll skip that. The newer algorithms we like to use now, the cooler kids on the block, are the Salsa family of ciphers. So Salsa 20 is the first algorithm. Char 20 was followed up because it's a bit more optimized for how CPUs do it. The main advantage of these algorithms is the implementation only uses bit shifts, like wraparound bit shifts, arithmetic shifts, and addition, which in cryptography means addition, usually means bitwise addition, which we just call XOR. That comes up all the time where you just see add and you have to check if it's the right kind of add. This means you don't need weird instructions to calculate it fast. It can just be calculated fast on any computer. I'd recommend it if you don't have AES hardware, which a lot of smaller chips will have. You can also turn down the algorithm. Salsa 20, the 20 returns to the amount of times you iterate. There are actually a Salsa 12, which is faster, but only use it if you're real desperate. And there are variations on these algorithms that make it a bit easier, but you can look them up. Sorry. Okay. This one's really annoying to explain. I don't think it's that annoying. Public key cryptography is, for a long time to me, was very confusing. Because how do you have a key that's public? But it solves a key problem that we just had. The previous algorithms I just mentioned are all symmetric. You have a key as your input. It's usually a fixed size, say 256 bits. But in order to send a message to someone else, they have to already have the key. And you run into a problem of How do you give them the key if they're on the other side of the planet and you don't already have an encryption method, in which case you wouldn't need to exchange the key? So some very smart math people came up with public key cryptography, which with public key cryptography, you'll have an algorithm. It has two keys, a public key and a private key. The private key is kept secret, that's why it's private. The public key you can share with anyone, and they can encrypt your data and encrypt the key and send it to you, and then encrypt the message. There's a lot of choices for public key algorithms now, the most well-known of which is RSA. RSA is okay, but it's very hard to implement because there's a lot of gotchas in it. Is in the RSA wiki, you'll see hundreds of little variables, it's like 10 variables. Some of them, if you get them wrong, it's trivial to decrypt. So sorry, I don't think I can keep going. Does anyone have any questions about what I covered? You can clap if you want. I'm going to turn this off. Plug you in. We have questions, amazing. Hey, what? Technology worked. Amazing. The microphone is having fun. Oh, we have a working.
Okay, we have a working microphone. All right.
Kip.
Thank you for the talk, Triss. I actually learned some things I didn't know even after 30 years of doing crypto.
Yeah.
Is there any resources you'd recommend to someone who's wanting to, I guess, know the pitfalls and the Cliff's notes on using crypto safely?
Using crypto safely is a hard question. One place to just start is try with libsodium, try to look what it lets you do, and then go, why doesn't it let me do this thing? And then I went down a rabbit hole and find out. One of the examples is the symmetric algorithms it provides. I was trying to encrypt a very large file, and it would only let me encrypt it, decrypt it, or encrypt it all at once. And I was like, I know with this algorithm I was using, so NaCl is developed by the same person as Salsa 20 and Char-Char 20. So his libraries naturally provide it. But with NaCl and libsodium, it doesn't let you do the whole thing at once. But it only lets you do the whole thing at once, and the answer was it's also authenticated, which means that it makes sure that it wasn't corrupted or anything. So there's reasons you do that, but you never want to let the user actually use partially decrypted data because of that corruption. That was one place I learned things. Can't think of any great resources for making sure, because if you start looking at these things, you'll keep running into information that is incorrect. And I've just had to learn that through a lot of different resources. I do have a podcast I can recommend, but it is very dense podcast. Yeah, that's what you do. Security, cryptography, whatever. Don't rely on the Wi-Fi during talk. Um, I can't think of anything else, sorry.
Okay, we've probably got time for one more question.
Yeah, thanks for your talk. I really love your approach of trying to make it more accessible.
Yeah.
And on that theme, is there any places or software that you sort of wish there was a bit more encryption, or you think are sort of not doing the best job?
Yeah. I wish it was like just easier to like have like a normal library that can just say do the encryption for me. Because even with Sodium and so on, which make it pretty simple of just encrypt my data and keys, you have to do a lot of work on making sure you handle the keys correctly and all these other things. And one of the problems, like we're talking about design in our APIs, is it would be easier to just do OAuth 2 using, it wouldn't be easier, it would be more secure if we used, instead of API keys, is use public key cryptography. It kind of sign your messages. And that means we never have the keys, they have them. But the problem is getting developers to just handle the keys themselves gives them a lot of work to do, and it's extremely hard to do correctly. But it would be easy if there was just like an OS API, say, store my key please, don't lose it.
But then at that point they're not using the REST API, but they would be doing a lot more secure.
Yeah.
Yeah, right.
It'll still be through REST. OAuth has a implementation, it just goes in the header. You use the public key cryptography to sign your messages as you send them, and that prevents a lot of attacks that API keys do not prevent. Yeah. So it'd be a lot easier if you could have like key synchronizing. Passkeys don't really let you use the keys, but if they added that, it would help. It's just always whenever you try to reach out to cryptography, you do have this layer of like opening a library that says, oh, use the AES char blue blah x poly 1305. That didn't actually make sense, but you wouldn't be able to tell, would you? You need someone who's already gone through the pain of reading a lot of jargon to understand what each thing does. libsodium does this a bit better, it just says cryptobox, but it helps. But libsodium's not always that accessible, so.
Thank you very much, Triss.